In this video, I'll cover the basics of feedforward neural networks. I'll talk about the intuition behind their design, followed by a diagram of their flow from start to finish. I'll introduce the concept of deep learning, and then finally, I'll make some comparisons between neural networks and traditional classification models. Feedforward neural networks are the earliest and simplest form of neural networks. The way they work is pretty straightforward. Data is just fed forward from one layer of the network to the next, all the way from the beginning to the end of the network. Each layer in a feedforward neural network contains one or more units, and each unit in a given layer receives input from every unit in the previous layer and sends output to every unit in the next layer. This is often referred to as being fully connected. However, a unit in a given layer N does not receive information from or send information to any other units in its same layer. The outputs of all units in a feedforward neural network, except for those in the last layer, are hidden from external viewers. Here's what the general flow of a feedforward neural network looks like. We can start out with an input, which for a neural network would be some kind of feature vector and most typically a dense word embedding like word2vec or glove. We'll also add an output node here, which is going to predict a class label or some kind of output value. We'll add in two hidden layers. Notice that each of these hidden layers contains a few units, 3 in this case. We'll start connecting these layers to one another now. So we'll feed the input, and this is the entire input vector, so really it could be 300 different values being passed by each of these lines to each unit in the first hidden layer. Now we'll feed the output from each unit in the first hidden layer to each unit in the second hidden layer. And we'll feed the output from each unit in the second hidden layer to the unit in the output layer, at which point we'll be able to predict a class label. You've probably heard about neural networks before, and you've probably also heard about deep learning, and now you might be wondering whether neural networks and deep learning are the same thing. The answer is basically yes. People generally refer to neural network-based machine learning as deep learning because modern neural networks often have a lot of layers. Beyond that, the definition is a little hazy. It's hard to define how many layers deep really is. The network you see here probably wouldn't be considered deep because there's just a hidden layer and an output layer. But the network you see here might be considered deep, and the network you see here would definitely be deep. In reality, some modern neural networks have even way more layers than this. So we've learned a bit about neural networks and deep learning in general, but what really makes them different from the other classification algorithms we've talked about? In many cases, neural networks are more powerful than statistical models like naive Bayes. One key reason for this is that traditional classification algorithms usually assume that data is linearly separable. That is, if you lay the data out in your n-dimensional space, you can draw some hyperplane that would nicely separate it. In reality, though, a lot of data isn't linearly separable. Neural networks learn nonlinear functions, so they're often better able to separate classes in these cases. Neural networks also tend to use different types of features from traditional classification algorithms. While the classification models we've seen so far, like naive Bayes and logistic regression, have primarily made use of manually engineered features defined by system designers, neural networks mainly make use of implicitly learned features like word embeddings. Although neural networks are really popular and they're great choices for a lot of tasks, they're not necessarily the best classifier for all tasks. In general, learning high-quality neural network models requires a lot of data, and the deeper the network is, the more data it usually needs. So neural networks tend to work well for large-scale problems, but they can have limited or no advantages over other statistical models for some small-scale problems. It's often useful to experiment with both neural and statistical models when playing around with a new text classification problem to figure out what works best for your use case.